Hello viewers, today in this part of the presentation we are going to discuss electrical conduction in semiconductors. So, the outline for the discussion is we will first start with the discussion of electrical conduction in semiconductors, then what are the types of bondings which exist in semiconductor, then what is intrinsic semiconductor and the carrier density in intrinsic semiconductor, then the conductivity of intrinsic semiconductor, then we will discuss extrinsic semiconductor and two types of extrinsic semiconductors such as N type semiconductor and P type semiconductors, and in the end we will discuss about Hall effect. Conduction in semiconductors. Resistivity of semiconductors at room temperature lies between that of metal and insulator, and the resistivity is temperature dependent. So, if we put the semiconductor at liquid helium temperature, it will act as an insulator, but as we keep on increasing the temperature, the resistivity keeps decreasing. So, in another word, we can say that the semiconductors show negative temperature coefficient of resistivity. Now, semiconductors, as we say, are more like insulators when we consider them in room temperature, but the difference is in semiconductor the resistivity is lower than the resistivity of insulators. Now, the most common elemental semiconductors that we use for major applications is silicon and germanium, though there are many more elemental semiconductors present in the periodic table. As you can see in the image, there are these elements which are inside the box made in the periodic table, which are considered as semiconductor elements, but mostly, as we say, the used semiconductors are silicon and germanium. So, we not necessarily have elemental semiconductor, we also have compound semiconductor which are made up of combination of material of different groups in the periodic table. For example, lead sulfide is one compound semiconductor, similarly cadmium sulfide, cadmium selenide and so on. Now, if we look at the inner structure of these semiconductor elements, then most of these semiconductors they form diamond like crystal structures. So, because we are mostly interested in silicon and germanium, they also show diamond like crystal structure. So, in diamond like crystal structure, each atom is surrounded by 4 neighboring atoms, and these atoms are bonded with each other by covalent bond, which is formed because of a pair of electrons which are sharing the electron from their parent atom. Now, at low temperature all the valence electrons are bonded, but as temperature increases atomic vibration also increases and electrons get energy from vibrational energy to set free. Now, the electron which is free at a temperature greater than 0, and if we apply an electric field to the material, then we will find that the electron which is free is moving opposite to the direction of electric field. As you can see in this particular image, that the electron is leaving position A and going away from the electric field, and similarly electron from position B is coming to fill the position at A, and similarly electron from position C will come and fill the position at B. So, in this way electron moves in the opposite direction of electric field, and the blank space which moves, which seems like moving in the direction of electric field, they are called the hole, or the empty space are called as hole. Now, while moving the electron may get trapped in broken bond, or similarly new bonds may get broken. So, in pure element the total number of electron and hole is conserved. So, these particular materials where the total number of electron and holes are conserved are called intrinsic semiconductors. But when we dope these semiconducting materials with some amount of impurity, then the total number of electron and holes are no longer conserved. So, the number of electrons or the number of holes will be slightly higher than the other carrier in the materials. So, these kind of materials or these kind of semiconductors are called extrinsic semiconductors. Now, how to find out the number of carriers in the intrinsic as well as the extrinsic semiconductor? Let us first get to know how to find out the number of carriers in intrinsic semiconductor. So, we will discuss intrinsic carrier density. So, basically we have to use the knowledge of quantum mechanics and statistical mechanics to find out the number of carriers in intrinsic semiconductors. So, for this we have to consider the band picture of the solid, in which we have a conduction band and we have a valence band. The conduction band energy levels are higher than the valence band energy level, and there is a gap between the conduction band and valence band which is called the energy gap. Now, we can derive the carrier density in intrinsic semiconductor, and we can come up with this formula, that is N, which represents the carrier density, is equal to 2 pi m k T by h square to the power 3 by 2 into m e into m h by m square to the power 3 by 4 into T to the power 3 by 2 into exponential minus omega g by 2 k T. In this particular expression, m e and m h are the effective mass of electron and hole, and omega g is the band gap. Now, if we consider m e is equal to m h, and if we represent that as m, then at room temperature, if we consider the band gap to be equal to 1 electron volt, then the number of carrier density comes out to be 5 into 10 to the 16 per meter cube, but the number of atoms will be more than the number of carriers in the intrinsic semiconductors. Now, if we analyze this particular equation little bit closely, then we will find that the number of carrier density is predominantly dependent on the temperature which is present in the exponential part, that is the exponent temperature dependent part contributes more towards the number of carrier density, that is N. Now, if we plot the relationship between N and T, then we will get a straight line, and the slope of that straight line will give the band gap for the materials. Now, since conductivity of material is proportional to the number of conduction electron, so the conductivity also depends on the band gap of the material. So, this discussion can also be extended to compound semiconductors. Now, if we know Ne, that is the number of electrons and the charge of electron, as well as the number of holes and charge of holes, then we can find out the total conductivity of the material by following the equation, that is sigma is equal to Ne E square tau E by Me plus NH E square tau H by Mh, where tau E and tau H are the relaxation time of electron and hole. For intrinsic semiconductor, as we know that Ne is equal to Nh, so we can represent that equal to N. So, the mobility also can be represented as mu E is equal to tau E by M and mu H is equal to tau H by Mh for electron and hole respectively. So, our conductivity relationship will now get simplified to the following form, that is sigma is equal to Ne square into mu E plus mu H plus Ne square, or is equal to Ne square tau E by ME plus tau H by MH. Now, in intrinsic semiconductor, the charge carriers are scattered by lattice vibration. So, because we have already discussed what is the relaxation time. So, the relaxation time in these intrinsic semiconductor will depend on temperature, and that variation with temperature will be T to the minus 3 by 2. And if we plot the variation of conductivity with respect to temperature, that way the slope from the curve will give the band gap. So, in another way we can also find out the band gap of the material by observing the variation of conductivity of the material with respect to temperature. Now, so far we discussed about intrinsic semiconductor. Now, we will discuss about extrinsic semiconductor. As we started our discussion that extrinsic semiconductors are of two types, one is N type semiconductor and the other one is P type semiconductor. So, let us first discuss about N type semiconductor. So, carrier density in N type semiconductor. When a pentavalent impurity is added to silicon or germanium, it becomes an N type semiconductor. So, what are these pentavalent impurities? The example, very common example of pentavalent impurities are phosphorus, arsenic and antimony. So, with a very small amount of these impurities in the semiconductor will increase the conductivity manifold. So, the impurity atoms usually reside in the regular lattice position of the semiconductors. So, if a pentavalent atom is added, there will be an extra electron which is not bonded strongly to the parent atom. Now, this extra electron is very loosely bound to the impurity atom because of the dielectric medium, and the energy required to ionize the atom is approximately 0.01 electron volt. In the case of antimony in germanium, if we consider this case at absolute 0, then all antimony atoms will be unionized, and the electron of unionized impurity will reside in an energy level which is very close to the conduction band energy level of germanium. And when temperature increases, some electron absorb appropriate energy from lattice vibration. Hence, they will get excited to the conduction band. So, the antimony atoms are now called donor atoms because they are very easily donating electron to the semiconductor, and the electrons which are residing in the energy level close to the conduction band, and that particular energy level is called donor energy level. Now, when the temperature becomes very high, electron from the valence band will also jump to the conduction band. So, if the temperature is assumed to be sufficiently low, then one can calculate the number of electrons donated to the parent semiconductor. Now, if we assume Nd to be the number of donor atoms and small n is the number of electrons donated at a given temperature T, then Nd minus n will be the number of unionized donor. And it can be shown that small n divided by Nd minus n is proportional to exponential minus omega I by kT, where omega I is the energy gap between the donor energy level and the conduction band energy level. So, as temperature increases, n also increases exponentially. Now, if we keep on increasing the temperature, then when kT is greater than omega I, then all the donor atoms are ionized, and now we can say that small n is equivalent to Nd, that is number of charge carriers is equal to number of donor atoms. So, at low temperature the conductivity is mainly due to the electron of donor impurities, and as the temperature increases, the conductivity is mainly due to the electrons which are in the valence band of the semiconductor. Here we have shown in this particular image the variation of the number of charge carrier with respect to temperature. As you can see, as we increase the temperature, the number of charge carriers are increasing exponentially, and the three curves that are shown in the graph are at three different impurity concentration. Now, if instead of doping with a pentavalent impurity, if we dope with a trivalent impurity, then the semiconductor will no longer be an n-type semiconductor, it will behave as a p-type semiconductor. And some of the common p-type dopants are boron, aluminum, gallium and indium. And when we dope these trivalent dopants in the semiconductor of silicon or germanium, holes will be created in the absence of electron which are bound to the impurity atom at absolute 0. Now, electron will jump to holes and subsequent motion helps in hole conduction. The energy required for the electron to do that is the ionization energy of impurity atom. Now, at absolute 0, all holes will stay in energy level very much close to the valence band. So, this level is called the acceptor level. Now, as the temperature increases, let us say at temperature T which is greater than 0, electron will jump from valence band to acceptor level, creating hole in the valence band. So, the carrier density for p-type semiconductor can also be calculated in the same way that we calculated for n-type semiconductor. And here also we can show that the number of carriers divided by the total number of unionized ions is proportional to exponential minus omega I by kT. Here omega I is the energy gap between the valence band edge and the acceptor level. So, at low temperature, valence electron at acceptor level, and at high temperature conduction electron helps in conduction. Now, that we know the two different types of semiconductors and the number of carriers in those semiconductors, we can study a very exotic phenomenon called Hall effect. So, Hall effect is a very important experiment used to find out some of the very unique characteristic features of semiconductors, and some of them are the number of charge carriers in the material, or to know what is the majority charge carrier in the material. To find out the mobility of the material, we can use Hall effect measurement to calculate all these characteristic features. So, in this measurement, what we usually do is that we apply a magnetic field perpendicular to the direction of electric field, and because of this, there is a voltage which will develop in a direction perpendicular to both electric field and magnetic field, and this voltage which will be developed perpendicular to both electric and magnetic field is called the Hall voltage. As you can see in this particular image, that we have applied the electric field in the x direction and the magnetic field in the z direction. Now, the resulting force due to the electric field and magnetic field will cause the charge carrier to move, and the motion of the charge carrier will depend on what is the nature of the charge carrier, that is whether the charge carrier is an electron or the charge carrier is a hole. So, if the charge carrier is a hole, then it will move in the negative y direction, and if the charge carrier is an electron, then it will move in the positive y direction. Hence, a voltage VH, which is the Hall voltage, which will develop in the y direction, and we can find out an expression for this Hall voltage in the following way, that is VH is equal to RH Ix Bz by D. D is the width of the sample that we consider, and RH is the Hall coefficient, which is represented as 1 by Ne, and for electron RH is a negative quantity and for hole RH is a positive quantity. Furthermore, as we discussed that from Hall measurement we can find out the mobility. So, we can also write an expression for mobility, that is mu E is equal to sigma by Ne, and in terms of Hall coefficient it is equal to RH into sigma. So far whatever the Hall measurement that we discussed is a very simple experiment for materials which is really highly conducting. But if we consider to find out the Hall coefficient or the conduct or the mobility or carrier concentration for semiconductor, then things get little bit complicated, though it is not that complicated to find out all these parameters, but we have to consider few more parameters to find out all these characteristic features of the semiconductors. So, from this discussion what we can take out is the following. There are few points which are very important in the case of semiconductors, and that is we need to first understand what is the conductivity of the semiconducting material that we want to use. So, if we know the carrier density of the material, then we can use the material or we can use the semiconductor for different applications. As we discussed that the semiconductors are of two types, that is intrinsic semiconductor and extrinsic semiconductor. So, intrinsic semiconductors have some typical features which we dope them highly with a pentavalent and trivalent material, then we will eventually get extrinsic semiconductor of N type or P type materials. So, these N type and P type materials or N type or P type semiconductors also have typical features which can be observed when we do the conductivity study of these materials with respect to variation of temperature. And once we observe these features of the semiconductor, we can use them in one of the very important application or experiment, that is Hall measurement, and from Hall measurement we can find out three important parameters, that is the carrier concentration of the semiconductor, the nature of the charge carrier, and we can find out the mobility of the semiconductor. So, with this knowledge we can now use the semiconductor for various applications that we intend to apply in our day to day life. Hope this session would have given you enough idea to understand and explore more about semiconductor in the future. Thank you very much for your attention.